Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe assumptions of error. As we discussed in previous lectures, the choice of an estimator is influenced by our measure of error. These characteristics of estimators, unbiasedness, efficiency, and consistency, also depend upon some assumptions that we make about error. Specifically, we make the 4 assumptions that our error scores are normally distributed, unbiased, independent, and identically distributed. We've already talked about what normally distributed and unbiased mean, so let's talk about the other 2 error assumptions. IID stands for independent and identically distributed. Typically, independence and identical distribution go hand in hand, and people test for both, but I'll explain what each one is individually. This abbreviation is commonly used in statistics, and as I just said, these assumptions are often considered together as a package. Independence means that error is independent of the other errors in the sample. An example of lack of independence would be when we have scores grouped into higher order groups that might influence the similarity of scores to one another. Let's take a look at an example of this. Imagine we have 9 scores of reading comprehension for 9 students, and the students are from 3 different classrooms. The scores are listed below each student. We can compute the mean of these scores, which would be 86. Just looking at the raw scores, we can see that the scores in classroom 1 are more similar to one another than they are to the scores in classroom 2 or classroom 3. The scores in classroom 1 all range around the mid-80s, the scores in classroom 2 are all in the high 90s, and the scores in classroom 3 kind of range throughout the 70s. So within each classroom, the scores are more similar. This could be because the teachers use different teaching styles. One class is for remedial students, they come from different grades, or a variety of other reasons. When we calculate the error, or the raw score minus the mean, we see that the error scores are also more similar to one another within classrooms than they are to error scores coming from other classrooms. I now show the error calculated on the bottom of the screen using the mean of 86. The independence assumption says that no error score should be more similar to another score or group of scores than any other. They should all be independent of one another. If we did have such scores grouped into classrooms like this would violate the independence assumption, and we would have to use a different statistical framework to look at this data. Now let's talk about the assumption of identical distribution of errors. This simply means that all errors come from the same distribution. This means we assume all members of each sample come from the same population, and so their errors will be somewhat similar. We won't find any comparatively huge or tiny errors. Remember, we talked about outliers, or very extreme scores. These would result in comparatively large error values, resulting in a violation of this assumption. Another way to think about this is that an outlier's error has to be really large to affect results from an analysis. Related to this assumption, the identical distribution assumption, is the assumption of homogeneity of variance. When we are examining group differences, we make the assumption that the group typical errors, such as variance or standard deviation, are relatively equal. Sometimes an experiment will result in one group having significantly larger or smaller typical error than another group. If the group typical errors are not equal or close to equal, one group will influence the results of the analysis more than the other. A larger typical error in the larger group will result in a larger test statistic. A larger typical error in the smaller group will result in a smaller test statistic. This influences the statistical power of a test. Unequal group variances would be a violation of the homogeneity of variance assumption, and this is known as heterogeneity of variance. This concludes part 4 on models of error and distributions. In the next lecture, I'll show you how to compute and interpret z-scores.